Okay, let's talk about Chapter 5, Newton's Laws of Motion. It is a very important chapter and a fundamental chapter for the rest of the semester, or the rest of the first 10 to 13 chapters of this book. So please pay attention to this. It is very important. Newtonian mechanics. So kinematics in general describes the motion, and dynamics describes changing of the motion, okay, whatever the cause of those. And these are mostly developed by Isaac Newton, Sir Isaac Newton, in mid to late 1600s. So we have that's why we have the Newton's laws of motion, and they're not derived, but they've been deduced from experiments. So in other words, these laws are laws that he found by doing experiments and not just by driving the mathematical version of them, okay? So let's take a look at them. Force. So force is causes a change in an object's state of motion. For example, push or pull, which are different types of the contact forces. So that's what we have here. Interactions between two objects. It could be action and a distance force, for example, gravity. So what we have here is gravity is an example of that, okay? When we say force, we're implying a net force, okay, or a total force acting on an object. It is a vector. It is very important to remember that. Force is a vector, okay? It's a vector. It has a magnitude and direction. So, for example, push down on a box or push horizontally on a box. It has a units of newtons, and 1 Newton is 1 kilogram times meters per second square. So that's also something to remember and have in mind. Okay, mass and force. So the ratio of the magnitude of the net force and acceleration is constant. In other words, if you have the net force acting on an object, which I will just call it F of net, okay, if you divide that by the object's acceleration, this ratio is always constant, always, no matter where you are in the universe, and this is called mass or inertial mass, okay? So this I unit of mass is kilogram. It's not gram, it's not pound, it is kilogram. So 1 kilogram is the mass of the cylinder of platinum iridium alloy kept in the vault in Paris, okay? This is also something that we covered in Chapter 1. So use kilogram to define the Newton. So 1 Newton is the amount of net force that gives an acceleration of 1 meters per second square to a body with a mass of 1 kilogram, okay? In other words, if I want to write down something like this, in this format, if I have F of net equals mass times acceleration A, okay, I can write it like this. F of net of 1 Newton. So 1 Newton is 1 kilogram object being accelerated 1 meters per second square. Okay, now we have other systems of units, okay, and it's important to remember that the one that we are using is this one, SI, or a standard system of measurements. In the standard system of measurements, or SI, or metric system, in other words, we have the Newton for force, we have kilogram for mass, and we have meters per second square for acceleration. So just keep that in mind. We have other systems, but we are not using them, right? As I said, force is a vector. Okay, so we have to draw an arrow, for example, to define and to show that vector. So arrows are used to represent forces. The length of the arrow is proportional to the magnitude of that force. So if you have a 5 Newton force here, for example, all right, and then you have 15, so the 15 is approximately 3 times longer than the 5 Newton. So it's important to draw, and when you're drawing a force, it's important to have the right proportion for them. All right. Drawing force vectors. So use a vector arrow to indicate the magnitude and direction of the force. Okay, for example, you are a 10 Newton pull directed 30 degrees above the horizontal. Okay, so you're showing your force with an arrow like that, starting from here, starting from this point and ending up that point. And this is a 10 Newton above 30 degrees above the horizontal. And a push directed 45 degrees below the horizontal. So it looks like this. In other words, this is, let me show it this way. So this is the horizontal of the guy who is pushing it, and then that means we have a 45 degree here, 45 degree angle here, which is the same essentially to what you can see here on your screen. It's 45 degrees above. So this is a push force acting on a box, all right? And remember, now that you're looking at this, if you remember chapter 3, what we talked about is that we can, break down these vectors into their components. So all of these vectors, a 10 Newton vector, 30 degrees above the horizontal, has a x component, okay, and has a y component. And the same for this guy. This guy has a x component and y component. They are vectors, so depending on where you are choosing your coordinate system, they will have a x component and a y component. Okay, we'll get to those in a little bit. Okay, let's talk about Newton's first law, the law of inertia. So an object, so this is the first law. An object in constant motion in a straight line will remain in a constant motion in a straight line, and an object at rest will remain at rest unless acted upon by an outside, or, in parentheses, and put an emphasis on it, a net force. Okay, the net force is a vector sum of all the forces acting on the object. All right, so in other words, if an object is moving with a constant velocity, it means that if there's no net force acting on it, it will continue to do that forever. And if an object is staying at rest, it will stay at rest unless acted upon by a force. For example, let me give you an example. You're probably watching this video on your phone or your computer, and if you have your pen on in the table, that pen is staying stationary without any type of motion, unless you push it, you pull it, or whatever, unless you act on it or unless you apply some force to it. So then it will start moving. Okay, so an object at rest will remain at rest unless acted upon by an outside or innate force. Okay, all right, let's take a look at this little example. So Newton's first law. A hockey puck slide on ice at constant velocity. What is the net force acting on the puck? Okay, what's the net force? So what we know is that it is going with a constant velocity. So let me actually go ahead for a second and highlight that because it is important. It's going with a constant velocity. Okay, so that means the velocity is not changing with time. All right, so that means that velocity is a constant value, okay? And that means there is no acceleration then. So acceleration is 0. All right, what is the net force acting on the puck? There is no net force acting on the puck. Let's go back to our definition of the first law. An object in a constant motion in a straight line will remain in constant motion in a straight line. An object at rest will remain at rest unless acted upon by an outside or net force, which is exactly the same thing here. All right, so the net force acting on that, as long as it is moving with a constant velocity without any change, it will be 0. Now, in reality, we know that this is not the truth in hockey, right? Because there's always a friction with ice, even though it's really, really small, but we know that it's there, it's not 0. So this is not a 100% truth when it happens in our daily life, because we can't avoid friction. But in physics, oftentimes we think that way. We think that there is no friction. So Newton's first law, let's take a look. An elevator is being lifted at a constant speed by a steel cable attached to an electronic motor. So there is no air resistance, nor is any friction between the elevator and the walls, any friction between the elevators and the walls of the elevator shaft. The upward force exerting the elevator by the cable is so. Let's highlight the most important parts. Constant speed, okay? There is no air resistance. Obviously, we avoid that in physics, especially for basic physics. There is no friction between the elevator and the walls of the elevator shaft. So there is essentially, we are avoiding all the frictions. So the upward force exerted on the elevators by the cable is greater than the downward force by gravity, equal to the force of the gravity, less than the force of the gravity, any of the above depending on the speed of the elevator. So we obviously can eliminate this one. D is absolutely incorrect. So let's take a look. It is going with a constant velocity. That means that there is a force upward acting on this object, okay? And there is another force because of the gravity. So the force of the gravity, F of gravity. And this other force is because of the cable, okay? So if it's going with a constant velocity, no net force should act on it. Okay, so no net force. All right, that means the F that is going up should be equal to force of gravity. Okay, so B is the correct answer. We also should know that we have to have a frame of reference. So an inertial reference frame is the one in which Newton's first law is valid. Okay, it means that it is not accelerating. In other words, let's take a look at A to C. So here we are initially in a vehicle. Initially, the vehicle or this wagon is at rest, and then so it start moving with the acceleration of A towards right, and then so you're gaining the box or the wagon's gaining speed as it moves, but you are wearing a skate or staying at the same spot at the same time because you're relatively not moving with respect to the ground. Okay, but once you get back there, let's take a look at B. Okay, if the wagon or a train is decelerating, it's losing speed as it's moving on, then that it means it has an initial velocity of v, but then it's losing that v until it gets to stop. But you are moving with the same velocity. You are moving to the right with the same initial velocity. If we are considering that there is no friction between the wheels of the skate and the floor of the train, then you are going with the constant velocity towards right. You tend to continue moving with constant velocity as the vehicle slows down around you. It's the same thing if it's turning, because we know that turning or going around a circle is also creating a type of acceleration for you. So remember, an acceleration happens if the magnitude of velocity is changing or the direction of the velocity is changing. So either acceleration is either the magnitude of velocity or direction of velocity is changing. And this is exactly part C. Is a vehicle round a turn at a constant speed, but you are going straight, okay, because of the inertial reference frame, okay? Or in other words, let me give you another very, very cool example. Let's see, let's say that we have a train, and let's say that this is our train, let's say. Can we use this? Yes, let's do that. Okay, so these are the wheels. And let's say that you are this guy right here. So this is you. And this is your friend, okay, who doesn't care. He wants to go and sit on top of the train. And the train has a mass m. And let's say that the mass of your friend compared to the mass of the train is almost negligible. So we can get, we don't consider that. And if you want to write down the Newton's law, you will write it something like this. So what you are writing is this. You say that the net force, okay, is the mass times the acceleration. This is the Newton's second law. We haven't get there yet, but I'll explain it because it's important to understand when we're talking about the inertial reference frame, okay? Now, if you want, you can go a little bit ahead of this video and watch the Newton's second law, okay? And then come back to this part to understand it fully. But let's go over it. So this is the Newton's second law, but we'll get to that in the next couple of slides, right? So F net equals ma, and that is what you are writing because you see that the train is moving to the right, for example. So you see that the train is moving to the right. So you're assuming that there is a net force acting on the train, which is equals to m, its mass, times the acceleration. Okay, so this is what you are writing down as Newton's second law. When you are looking at the same Newton's second law, the same law, but from the point of view of your friend, which is on top of the train, okay, then what your friend is writing is this. F of net is 0. That's what your friend is writing. Because he's on top of the train and the train with respect to him is not moving. Okay? The train is not moving with respect to him. For example, if you're driving the car is not moving with respect to you. Okay, you are sitting in the car and the car is staying in the same spot with respect to you. So the car is not moving with respect to you. Same stuff here. He's on top of a train and the train is not moving with respect to him. So he think that since the train is not moving with respect to me, there has to be no net force acting on it. Remember the first law? Object at rest will remain at rest unless acted upon by force. So since this train is staying still, so there's no force acting on this on the train. Okay, so which one is the truth? We're looking at the same. We have to have one physics. Is that right? Yes. We have to have one type of physics here, but which one is giving us the truth? Okay. So when you are writing the Newton's law, you have to write it in a inertial frame. An inertial reference frame is not moving, not accelerating. See, this is the inertial reference frame. Inertial reference frame is this guy. It's you sitting out here, not moving, not accelerating. Okay, not accelerating. It's not moving. For your friend, for your friend which is up there, the Newton's second law, which is looking like this, is not valid. If you want to make it valid, you have to consider another type of force. Okay. All right. And that force is acting on your friend. So we have to consider another force acting on your friend. Okay. Which is negative mg, or going that direction. And if that, at that point, if you want to write the Newton's second law, then F net minus mg for your friend is 0, and then F net equals mg. Only if you consider another force acting on your friend, which is equals to negative mg to the left, then you can write the Newton's law without, sorry, it should be ma, not mg. It has to be ma. A is the same type of acceleration. A is the same acceleration as the train. So it has to be ma, not mg. This is ma. Get rid of that. Correction. Okay. All right, so you have to consider another force, which is ma to the left, if you want to use an accelerating reference frame. But for this course, you are only considering the Newton's second law once it is considered as a inertial reference frame, or a reference frame that is not moving with the object. Just like you sitting here looking at a train moving. You're not moving with the train, or you're not in the car moving. You are on the ground, staying still, not moving, with a velocity of 0, with an acceleration of 0, excuse me, with an acceleration of 0, watching your friend moving with the train. At that point, you can write the Newton's second law without any problem. Okay, so just keep that in mind. Now, let's take a look at this. You put your book on a boss seat next to you. When the boss stops suddenly, the book slides forward off the seat. Why? A net force acting on it, no net force acting on it. It remains at rest. It did not move, but only seemed to. So let's take a look at. Let's take a closer look at the problem. You put your book on a bus seat next to you. When the bus suddenly stops, the book slides forward. So the bus was moving with the constant velocity. Now it's going to stop. So it's losing speed because of the acceleration. But the book is moving with the same type of velocity forward. So that's why there's no net force acting on this object. It's exactly the same as this. It is exactly the same as part B. Okay, a train is stopping, but you are moving with the same type of velocity forward. It's exactly the same problem. Newton's second law, okay? And we already a little bit talked about it here, right there, but let's take a look at it here now. Okay, so sum of all forces, net force, on an object equals the mass times the acceleration of the object. So the acceleration produced by a net force on an object is directly proportional to the net force, is the same direction as the net force, and is inversely proportional to the mass of the object. Now, acceleration, in other words, acceleration is force acting on an object divided by its mass. Now, if I want to write it a little bit more mathematically, in a better format, I'll write it F equals ma. You might have seen this before, you might not, but here it is. This is the best way to show the Newton's second law, F equals ma. A force acting on an object equals to its mass times its acceleration. Okay? So, using consistent units, force will be Newton. So, remember, F equals ma, right? F is Newton. Mass is in kilogram. A is in meters per second squared, right? That's what it is. So that's what we have it here. So mass in kilogram, acceleration meters per second square, that will be 1 Newton or a Newton. If the force applies to a block is tripled, what happens to its acceleration? So if I multiply this F by 3, mass is the same anywhere else in the universe. It's always the same anywhere in the universe. So that 3 should be applied to A. If the same force is applied to 3 blocks, what happened to the acceleration? Think about it. Now you are applying the same force to 3 blocks. If you want to acceleration 3 blocks as much as 1 block, how much force must be applied? So let's take a look. So it triples, okay, again, F equals ma. Okay, so if you multiply F by 3, you'll get A equals multiplied by 3. If you apply the same force to 3 blocks, your acceleration will be 1/3. And if you want to apply the same acceleration to 3 blocks as much as of 1 block, then you have to triple the force, okay? So, using Newton's second law, so 4 important concepts. Vector equations, remember force is a vector, must split motions into components every time. That's why we had chapter 3, because now we're dealing with vectors, or we're dealing with force, and we know that we have to, break it down to its components along x and along y. Second, external forces only consider the forces acting on the object, not those that the object produces. So acting on the object, not those that object actually produces. Mass, only value of mass is constant. If the mass of an object is changing, for example, it's moving towards the positive x, but it's gaining mass as its move, just like a snowball effect, like a snowball. It's moving, it's gaining mass. So that is not, we can only apply this type of laws to a constant mass. Frame of reference, only valid in an inertial frame of reference. As you saw in a non-inertial reference frame, the object moving with the train, a reference frame moving with an acceleration, you can't write the second law, okay? So Earth is a close approximation to an inertial reference frame. That's why you have to consider the ground to be a reference frame for you. and we'll treat it as such. So, free body diagram. This is also very important part of this chapter. Free body diagram. It is unbelievably important. I have three resources for you that I will soon talk about them, and I encourage you to take a look at them. All right. So free body diagram. We'll continue that in the second part of the video. So stay tuned, and we'll continue with part 2 right away.